lollipop, lollipop, lollipop.
Wow.
You know the people were singing so fast that I didn't get
Okay, great. Yeah, just now earlier today we
it.
saw
I
at
haven't even.
yeah, so we all please return to your seats. Right, earlier we saw here, okay, at the two molecules.
Sulfur hexafluoride.
Yes.
And something penta, phosphorus pentafluoride.
Yes, phosphorus and chloride. You need to know how to name them. So okay, put down the name. So phosphorus, pentafluoride. So penta because they are 5. Yeah. Okay, and similarly, the compound on the right should be called sulfur, or yeah, you can spell it as SULPHUR, the UK spelling, or SULFUR, the US spelling. Okay, I prefer spelling the UK way. So sulfur hexafluoride. So remember, this is that very interesting gas. Okay, that when you breathe it in, it will make your voice really deep. Okay, so you have PCl5, SF6. How are these expanded octet species? So can you tell me, when you draw the structure out, which atoms here is violating octet rule? Is it P or is it Cl?
P.
P, okay, by having 10 electrons in the outermost shell, P is violating octet rule. So can you put down 10 electrons in the outermost shell of P? Therefore, it violates octet rule. For sulfur, this is even like a worse. Okay, how many electrons are there around sulfur?
12.
12. Because one bond means 2 electrons, right? And you see 6 bonds. That means there is a total of 12 electrons in the outermost shell of sulfur, which is also more than 8. Okay, more than the octet rule allows. So therefore, back to the 2 exceptions. Remember, we say when you have more than 8 electrons in the outermost shell, you belong to this class called expanded octet species. When you have less than 8 electrons in the outermost shell, you belong to the incomplete octet species class. Both of these molecules, both of these classes of molecules, they violate octet rule, but yet they exist. They exist. Most of the molecules, they are like these yellow ones. Okay, so they obey octet rule. They have 8 electrons in the outermost shell. So because these are exceptions, okay, so you know these are not exceptions. They play by the rule. And these 2 are exceptions. Exceptions are exceptions. You need to memorize them. Okay, they break the rules, but yet they exist. Okay, so the next thing we'll turn to is after we learn that PCl5, SF6, they are like some species that will violate octet rule. We need to introduce a new concept. It's called the VSEPR theory, okay, which we can use to predict the shape of molecules. So let me put this on a new page. How do we describe the shape of molecules? When we draw H2O, and let me put down the header here, the title here first. Predicting the shape, there may be, you can open the window if it's too long. I don't have a remote. We used to have a remote.
It's right there,
Go anyway.
Behind you, sir.
Oh, here, okay. Last lesson it was not here. So you need to. So you're getting told later now. So predicting the shape of molecules. Okay. First of all, when you look at the molecule CO2, what does it look like to you? It's like a rod, right? It's like a stick, right? Looks like the alphabet I. So we say CO2 is a linear molecule because it is straight. Okay, so we say it is a linear molecule. H2O, however, is a band or V-shaped molecule. Okay, because it looks like this. Looks like the alphabet V. Okay. But then you may be wondering, can I draw H2O like this? Well, it's going to H2O like this, right? And maybe you think that, does that mean H2O is a linear molecule then? Well, no. We will see. There are rules that determine the shape of molecules. We call this the VSEPR theory. Okay, so put down the correct statement first.
That's right.
H2O is a band or V-shaped molecule. So if you think that it's just a matter of personal liking, that you either draw it like this or you draw it like this, then you're wrong. These are not the real shape of CO2 and H2O. These are the correct ones. Okay, we'll look at the rules. We'll look at the theory that predicts the shape of molecule. The name of this theory right now is called VSEPR theory, okay, or VSEPR. I know this word cannot be pronounced, but yeah, we were just forcing a name all of these five letters. So valence, shell. The name of this theory is unimportant. It's how you apply it that is important. So if you can't remember what these five words stand for, forget about it. Just know how this is applied. We call it VSEPR theory. In a nutshell, okay, it says electron pairs in a molecule will repel one another. I will show you a simulation, and I assure you, everybody will understand it when I show you that simulation. Okay? But bear with me first. I will just put down the definition here first. Electron pairs in a molecule, which can be bond pair or lone pair. So bond pair and lone pairs. You all remember what bond pair and lone pairs are, right? Bond pairs are found between atoms. Lone pair are found on a particular atom, not shared. Okay? So that's bond pair and lone pair. They are collectively known as electron pairs. Electron pairs in a molecule will repel one another. This is where the word repulsion comes from. So will repel one another until they are furthest away possible. There's a bit of math here, so I want you to be careful now, and careful. So we repel one another until they are no, they are furthest away possible. Furthest away possible. So I think the simulation speaks like more than words. Okay, so why don't I show you the simulation straight away? So this is the simulation. So just a second. It's the same one we used earlier. Okay, but then let me use the model here. What do you see here? The two white blobs, okay, represent electron pairs. Okay, they represent atoms. The stick represents electron pair, bonding electron pair. Okay, I forgot to bring the tripod, but you can see that very thin stick, white stick between the purple sphere and the white sphere. Those are the bond pairs. And what does it look like to you? It looks like a rod, right? Currently, that's because the two thin sticks they repel one another until they are furthest away possible, which has an angle of 180, right? I think we can all agree that this is 180. What happens if there is a third bond? Okay, you see this molecule has two bonds, right? How can I divide 360 into 3 equal parts? What will be the angle between each of the bonds if there are 3 bonds? 120. Because 360 divided by 3 is 120, right? So what will happen when I add an extra bond? Can you see that they will still try to maintain distance from one another, and this is the furthest they can get. But then the next one, most students will answer it wrong. What if I have 4 bonds? So if I have 2 bonds, dividing 360 by 2 would give 180. You may make it 90. Okay? 360 divided by 4 is 90. But you have to also consider the fact that, what about the 3D space? When you add a 4th bond in here, yeah, you don't just have 4 bonds on the same plane. They can be 3-dimensional. Yeah, in this case, the angle will be 109.5. So you can make it your math homework. You can in fact prove this angle. You can prove that this angle is 109.5. I'm not going through the proof with you. I'm not saying math, but this is a math question. Here, can you put down? The electron pairs in a molecule will repel one another until they are furthest possible. So let's start with H2. Let's start with CO2 first. So CO2 has how many bonding group in here? There are 2 bonds, right? Or you can say 4 bonds if you consider like the double bond here and double bond there. But there are 2 groups of bonds in here. These groups of bonds, they will repel one another until they are furthest away possible, which is 180. Okay? So why can't I draw CO2 like this? Remember this wrong drawing I showed earlier? Why can't I draw CO2 like this? Because if you draw CO2 like this, would this angle be smaller than or greater than 180? Smaller than, and you see the wording I use here, right? They have to be furthest away possible. Less than 180 doesn't cut it. Yeah, I like to think of it this way. Look at these two bonds as like two persons who hate one another. They want to be as far away from one another as possible. If you move them any closer, they will protest, you see. If you move them any closer, they will protest more. And they will say, oh, I don't want to see it. Okay, so then, if you move them further apart in this configuration, they are happy. Because they are furthest away from the other guy possible, right? Now, what happens if I have, so right now, why is this the correct shape? This is correct because 180 is far enough. So it's far enough. Why is this an incorrect shape for CO2? That's because this is an angle less than 180. Okay, so less than 180 is not far enough. Okay, the keyword here is furthest away possible. So it's not far enough. Now, what about other molecules? Remember the electron deficient species? What are the three electron deficient species we mentioned in our previous lesson? The incomplete octet species.
Incomplete.
BeCl2.
Phosphorus.
Oh, electron deficient species, not the expanded octet species. We have BeCl2.
Beryllium chloride.
Yeah, beryllium chloride. BF3 and AlCl3. Yeah, so BF3. How do you name BF3? Trifluoride. How do you name BeCl2?
Beryllium chloride.
Beryllium dichloride. Okay, yeah, and or beryllium chloride. This one will be aluminium chloride. Yeah, aluminum chloride. So these are electron deficient species. When you draw BF3, why do you not draw it like this? Okay, let me put this in. Let me put that in correct shape first. This is what BF3 looks like. Why shouldn't you draw BF3 like this? Because if you draw it like this, what is the angle between the FBF angle? Is it far enough or is it not far enough? It's not far enough. The furthest angle, okay, that you should put the F and BF terms apart should be 120, right? So you know you have 120 degree here, here, and here. So 120 degree is far enough. But then when you have this configuration on the right, this is not good because it's too small, the angle. So similarly, if you have 4 bonds, okay, so 4 clusters of bonds. Okay, let me just show you a molecule. You all should know this. CH4, what is the name of CH4? Butane. Butane is C4H10. Methane is CH4. Okay, so remember what these lines mean, right? What does the wedge line mean?
Front.
It's front. It's pointing towards you. Okay, like out of the screen. The dashed line means it's pointing into the screen. Okay, into the piece of paper. So this is a 3-dimensional structure like this one. You see it here. I don't know why every time I have to read all. Okay, so can you see? This is what CH4 looks like. You have C at the center and you have 4 H's on the side. Okay, and when you keep adding, the shape will dynamically change. Okay, until the angle they will always be the furthest possible. You see. So if I reduce it back to 2, the angle is 180. When I add one more, they will try to move apart a little bit. Okay, and I know 120 is smaller than 180, but that's the best you can do, right? When you have 3 bonds. So you see, with different number of bonds, there is a different optimal angle. So these angles, unfortunately, you need to know them. And also you need to know the shape. Can you put down the name of this shape? When you see a straight line, when all the atoms line up to form a straight line, we call this a linear molecule. It's straight, okay? When you see atoms forming a triangular plane, like a piece of pizza, this is called trigonal plane. This shape, we call it trigonal plane. Don't invent your own term. Don't call it pizza shape or I don't know. Okay, yeah, no other terms allowed. In DMC, we don't allow this term. Trigonal plane, the name of the shape. Okay. What about, yeah, so you can spell it first. Trigonal plane. What about when you have 5 atoms, okay, forming something looking like a, what do you call this shape in math class? It's well, close enough. It's actually a tetrahedron. Do you know tetrahedron? Do you know what hedra means? Hedra means face. Face. How many faces does this shape have? 4, right? So you see, you have one face here, you have another face here, another face at the back, and then the last face at the bottom. 4 faces. So we call this shape tetrahedral shape. So this is tetrahedral. And the angle between the atoms is a very strange angle, 109.5 degrees. Okay, so this is far enough. So the takeaway message here is that when you have more than one bond, okay, more than 2 bonds, the bonding pair, they will try to arrange themselves as far away as possible, as they are negatively charged. Okay, so put down why they have to repel each other until they are furthest away possible. This is because, okay, both bond pair and lone pair, they contain electrons, and electrons are not charged, negatively charged. You know what happens when you put 2 light charged particles together? Do they attract or do they repel? They repel. So this is the basis of the theory. It's built on this simple principle that light charge electron, they repel. That's it. Okay, we are just giving it a very fancy name, VSEPR theory. But deep down, it just means light charges repel. That's it. Okay? So let's find it down now. This is because both bond pair and lone pair are electrons. Okay, so both bond pair and lone pairs are electrons, and electrons are negatively charged. So electrons are negatively charged. So negatively charged. So they repel each other. So they repel each other. So now I want to go through all the possible shapes with you. Okay, this is very difficult. Okay, but do you understand the theory here first? How it works? How it predicts the shape? Okay, we'll start from the basic on the right now. Yeah, this is just an introduction. So on the right, we look at let's define something simple first. Okay, A means the central atom. B means bond pair or bonding pair. E means lone pair. So lone pair, they are also known as non-bonding pair. So we can use these symbols to facilitate our discussion. Okay, so non-bonding pairs. Bond pair means bonding electron pairs. So we have non-bonding electron pairs. We have also bond pair, also known as bonding electron pairs. Let's look at a few examples and you will know what I mean by bonding electron pair and non-bonding electron pair. Consider this structural formula here, CH4. Can you tell me how many electron pairs are there around the central atom?
4.
4, okay, and they are all bond pairs, right? So you have bond pair here, bond pair here, bond pair here, bond pair here. What about in the molecule H2O? How many atoms are there around the central atom?
8.
How many pairs?
4.
4 pairs. But of these 4 pairs, how many are bond pair, how many are lone pairs?
2.
2 are bond pairs, 2 are lone pairs. Can you see that these are the bond pairs? And the remaining 2, they are the lone pairs, right? Okay, so we have, let's not call it bond pair, let's call it bonding domain. Okay, so bonding domain. And then we have lone pair domain. Right. So we have 4 domains on the left. So we have 4 domains on the left, of which all 4 are bond pairs. Okay, so 4 bonding domains. And on the right, you also have 4 domains. But of these 4 domains, 2 are bonding domains and 2 are non-bonding domains, right? Yeah, so bonding domains, you have two of them, and you have two non-bonding domains. Why do we have to distinguish between bonding and non-bonding domain? That's because we can only see the bonds when we inspect a molecule. It is the bonds that we can see. We cannot see the lone pairs. Because lone pairs, they are electrons, right? They're too small to be seen. We can only see bonds. So this is why when you look at the molecule here, I don't know why it always has to be low. Let me change two of let me change two of the bond pairs to two of the lone pairs here. Alright, okay. So you can see this very funny shape things in here. These are lone pairs, okay? And when I toggle on this option at the bottom right hand corner, you see molecular geometry here. You see that it's bent. You said it's bent. That's because when you look at this molecule, which is the part of this molecule that you can see? Remember, you can't see lone pairs. So what is the part of this molecule that you can see? It's this part, right? And what does it look like? It's a V shape, right? Or it's bent. So you cannot see these two groups because they are electrons. So lone pairs cannot be seen, okay? So you have to write this down. Bond pairs can be seen. So bond pairs can be seen. Non-bonding domains on lone pairs, they cannot be seen. Okay, so when you draw this molecule out, okay, CH4, what does it look like? So you have C, and then you have H, 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 H. So all four domains around the carbon, they can be seen. Okay, so what is the shape of this molecule? Do you remember the name of the shape? Remember, this is not pyramid, this is tetrahedral, right? Just now. So tetrahedral. What about on the right? When you look at H2O, so we have H2O looking like this. So you have the lone pair here, another lone pair here. So these funny shapes, they represent lone pair. They cannot be seen. So which part of this molecule can you really see with your naked eyes? Only this part, right? So what is the name of this shape? It's bent or V shape, right? Yeah, it's just bent or V shape. So you can put that V shape or bent. As you cannot see the lone pairs, okay? So they are not visible. So you ignore them when you determine the shape, okay? So, and now I want you to remember how the domains will arrange themselves when there is a different number of domains, okay? So, how we copy this on the table. So the number of domains and how they arrange themselves. So how they are arranged in space. So if you have two domains, the two domains will be how many degrees apart? If you have just two domains, if you have just two groups of electrons, how far will they be apart? 180, right? So can you draw two domains here first? So this is when you have two domains. The two domains will be 180 degrees apart. When you have three domains, the domains will be how many degrees apart? 120, right? Yeah, so it will be 120. So you have 180 here, 120 here. What about when you have four domains? What was that real angle again? It's 109.5 degrees. Do you remember this angle from before? Yeah, I know this is a very weird angle, but you have to know how they arrange themselves. And then we are not done yet. There are two more. What about when there are four? What about when there are five? I mean the name of the shape. So you see when there are two, what is the name of this shape? This is linear. Remember? When you have three domains, this is trigonal planar. When you have four domains, this is not pyramid but trigonal, but tetrahedral. Yeah. Now we can phase out a notch. They can be 5 or as many as 6 domains. Okay, so the 5 domains look like this. I will show you a model. Don't worry. So this is how have the 5 domains arranged themselves in space. You can think of this as like an extension of the trigonal pyramidal thing. Imagine that I am inserting this thing over here. And then on top of this triangular, like a shape, I am adding 1 domain on top and 1 domain at the bottom. This is how I imagine it. The next shape with 5 domains is built upon that trigonal planar shape there. So in that, this will form the equator of the shape. And then you have like something like this. So the angle here, they really will not ask you much about the angle. Okay? It's only the shape that you need to know. Okay, so what are the possible angles here? What is this angle? 90. What are these angles? It's actually 120. Do you remember that I have inserted this green triangle into here, right? So that means all the angles between these purple blocks should still be 120 here, right? Between this and that, 120. Between this and that, 120. This and that, also 120. Okay? And then I'm putting another 2 domains on top and below this triangular plane. And because it is placed perpendicular, you know perpendicular, okay, to the triangular plane, this is 90 degrees. So the angle, if you really kind of imagine it, is fine. They are not asking you about the angle, they are asking you about the shape. And I'm here to tell you about the shape. This is a very complicated shape known as trigonal bipyramidal. So you know bi means 2. Okay, now the word you really like to use pyramidal is back, pyramidal. That's because you can think of this as, you know the pyramids in Egypt, okay, they look like this. Imagine that I have 2 pyramids stuck end to end. That's what trigonal bipyramidal means, okay? So you have 1 pyramid on top, so this part forms the top pyramid, this part forms the bottom pyramid. When you stick these 2 pyramids end to end, you glue them at the bases. This is the shape, called trigonal bipyramidal. Okay, you need to remember these yellow words, okay, they will appear in the exam. Finally, yeah, so just bear with me with this final shape. What happens if you have 6 domains? Well, no. This is called octahedral. Okay? So this is called octahedral. Right. Why is this called octahedral? Because hedra means face, right? You remember?
Yeah.
Why do we call that tetrahedral? Because it has 4 faces only. Now, this has 8 faces. Where are the 8 faces? Just focus on the top part of the pyramid first. There's one on the front, at the back, on the left, on the right. Already 4 faces. Let's count also the bottom half. There are another 4 faces, right? So, I don't know. So, for example, in here, you know the octahedral shape looks like this. Can you imagine a square-based pyramid first? Yes? Okay, so this square-based pyramid has how many faces? So this has 4 faces, right? This has another 4 faces. So 4 faces plus 4 faces means 8 faces. So this is why the shape you get out of it, we call it octahedral. Or it is octahedral in shape. Okay? Right. What are some examples of molecules that have this shape? Okay, we have, for example, SF6. So can you draw SF6 in here? S, and then you have F in here, and then you have another 2 F's here, right? So this is SF6. Okay, what is the shape of this molecule? Octahedral, right? So we say SF6, put down SF6 is octahedral in shape. Right? Yeah. And then I want to also help you understand the other shape, trigonal bipyramidal. What does trigonal bipyramidal mean? So you have a triangular base here. Yeah, you have a triangular base, and then there is a top half and a bottom half. So think of this as like 2 pyramids stuck end to end again. Okay, so first you have the top half, and then you have the bottom half. Okay, so you see this pyramid shape on the left is is equal to these two halves stuck together, right? These two halves stuck together. So because each of these is a pyramid, a triangular base pyramid, so we call this, so triangular pyramid. On top, you have another triangular pyramid at the bottom. Together, what do we call it? We call it trigonal bipyramidal. Bi means two. Okay, this word basically means there are two pyramidal shapes with a triangular base stuck end to end. So what kind of molecule has this shape? We have PCl5. Can you draw PCl5 now? So this is P, and then you have Cl, Cl, Cl here, and then there are two Cl groups, one sticking on top, one at the bottom. Okay, so can you make sense of this shape? I know it's very difficult to wrap your hands around, which is why now I will show you the simulation side by side. Don't worry. So put down the sentence first. PCl5 is trigonal bipyramidal. Let's take a look at the simulation, see if I can show you them side by side. Okay, apparently I can. Okay, so can you take a look at SF6 first? I will now remove the lone pairs. Okay, so we have 5 bond pairs. Okay, so these are where the 5 bond pairs are arranged. So can you see that? Look at the bottom left-hand corner. You see the word trigonal bipyramidal there. Okay. Trigonal bipyramidal. When I add or subtract bonds, you will see that this word will change. Okay? So let me copy this first onto your notebook. So we have PCl5 in here. This is the shape I was talking about, trigonal bipyramidal. Okay, so PCl5, this one. When I add one more bond, focus on the yellow one at the bottom left-hand corner. You see it changes to octahedral. Why is it an octahedron? Okay, because if you use some dotted lines to connect these atoms, okay, imagine that there are dotted lines connecting all the atoms together. You see something looking like an octahedron. There are 4 faces on top and 4 faces at the bottom. Okay, let me move it like this first, and then I'll copy it and I'll explain. So, right, so now I have this shape here. Okay, then I can go back to the simulation. So can you see that if I were to use some lines to connect these, like this, okay, I would get something that looks like this, right, on the left. So this is why SF6 is octahedral, because there are 4 faces. Okay, let me show you where the 4 faces are. There's one face here, another face here, another face here, and then another face at the back. 4 faces. Okay, at the bottom, 4 faces as well. 1, 2, 3, 4. 4 plus 4 means 8. Octahedral translates to 8 face, like a structure. Okay, 8 face structure. And why is it trigonal pyramidal? Because they have a triangular base. So you can see the triangular base in here. This is the triangular base. This is triangular base. They are glued together at the bases. Therefore, the name trigonal bipyramidal. I can't explain to you why these are the words we use, but I try to explain to you what they mean. Okay, you have to memorize these words. You can't invent your own term. You have to use trigonal bipyramidal or octahedral in example. Now let's just draw some lines connecting the atoms, and then you will see that this is indeed trigonal bipyramidal, right? I mean, when you look at this, you see the exact same thing we drew here. When you connect the dot, you see the exact same thing we drew here. Okay? So SF6 is octahedral, PCl5 is trigonal bipyramidal. Now, we need to look at something harder. Okay, what happens if I vary the number of bond pair and vary the number of lone pairs? Okay, so it gets harder. So VSEPR. And the type of electron, and the type and number of electron domains. So remember that there are 2 types of electron domains, bonding domain and non-bonding domains. So there are two types of electron domains. They are the bonding domains, which you can see, and the non-bonding domains that you cannot see. Okay, so these are non-bonding domains. So non-bonding domain means lone pairs. If you see one lone pair, that's a non-bonding domain. Okay, bonding domain is a trickier concept. It means any type of bond. A single bond is a bonding domain. A double bond is also a bonding domain. Yeah, maybe you wonder what does the word domain even mean then? Okay, domain means a group of electrons. Okay, so a domain means a group of electrons. So you know a single bond is a group of electrons, right? So it's a double bond. It's just a larger group of electrons, right? A double bond. Okay, but other than that, it should be treated the same way as a single bond, as a group of electrons. So it means a group of electrons. So bonding domain can mean what? It can mean single bond, double bond, or triple bond. Okay, so it can mean single bond, double bond, or triple bond. They are all considered as one domain. Okay, I know what you're thinking. Maybe you're thinking, why isn't double bond two domains? Why do we call it just one domain? Because the double bond is just a larger group of electrons. We don't take into account how many electrons there are. As long as there are electrons, we call it one domain. Having 4 electrons, or 2 electrons, or 6 electrons won't change the fact that it's still a group of electrons. Okay? So you have triple bond. Non-bonding domain can only mean lone pair. Okay, so it can only mean lone pair. So you have lone pair. So now, to check that you really understand the difference between bonding and non-bonding domain, here I want you to look at the molecules CH4, NH3, and H2O, and tell me how many bonding and non-bonding domains there are around the central atoms. Okay, by the way, in case I haven't made this clear already, we only care about the central atom and the domains around the central atom. The peripheral atoms don't matter. What are peripheral atoms? These are on the sides, they are the periphery. They don't matter. Only the O matters, N and C. Atoms at the centers are the only one that matter when we predict the shape. So the very, 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 very important note. When we use VSEPR theory to predict the shape, okay, so to predict the shape of molecule, we only focus on what is around the central atom. Everything on the side face into the background, we don't care about them. So we only look at what's around this is extremely important, okay, central atom. So from now on, I will mark the central atom in red so you can see it clearly. So this is the central atom. Central atom, central atom. Now a quick question. What is around the central atom here? Yeah, so can you tell me what is around the central atom carbon? How many domains are there around the central atom carbon? There are 4, right? So there are 4 bonding domains around the central atom. Okay, so there are, so around carbon, there are, we say 4 bonding domains. Okay. What about around nitrogen? How many bonding domains are there? Around nitrogen. How many bonding domains are there? There are 3. 1, 2, and 3, right? What about the remaining one? What do you call it? No pair or non-bonding domain. Okay, so can you put down? There are 3 bonding domains and 1 non-bonding domain. What about with H2O? 2 bonding and 2 non-bonding. Yes. Okay. So 2 and 2. So that means they all have 4 domains. So they all have 4 domains. When you have one domain when you have two domains, the domains will arrange themselves 180 degrees from one another. When you have three domains, the domains will arrange themselves 120 from one another. 4 will look like this. 5 will look like this. 6 will look like this. We already saw this on the previous page, right? This is how the domains will arrange themselves as the number of domain changes. So now you just have to put them back where they belong. So you see this gives 4 domains in total. The rest will also give you 4 domains in total. So this has 4 domains. This has all 4 domains, right? So therefore we will fill this in here. So this is what happens when you have 2 domains. So 2 domains, 3 domains, 4 domains, and then 5 domains and 6 domains. So 5 domains and 6 domains. Once you have decided that there are 4 domains, you can put them all into this structure here. So put them all into this structure. So let's try to draw this. First, we draw out a very large, like a 4 domain structure here first, and then we'll put back the atoms. Okay, so we have 3 examples to work out here. Starting with CH4. All 4 are bonding domains, so we will put, allow me to use the color white here, if not you cannot see. So you have C in here. So this is C, H, 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 H. All 4 are bonding domains, right? Do you remember which of these domains can we see, which we cannot see? The bonding domains, they are visible. Okay, so they are visible. The non-bonding domains, they are invisible. Okay, so these are invisible. So you cannot see them. So can you tell me, what is the shape of this molecule if you have 1, 2, 3, and 4 bonds here? You can see all 4 bonds, right? All 4 are bonding domains, which means you can see them all. So the shape of this molecule is therefore tetrahedral, yes. So you can see all 4 of the domains. So we say what we can see, okay, is tetrahedral. However, when we look at the second molecule, NH3, not so easy anymore. NH3 also has 4 domains, but unlike CH4, one of the domain is invisible. It is a lone pair. So we draw it like this. So we have a lone pair here, right? Now, pretend that we can't see the lone pair, cover it. Of course, I can't cover the projector, just ignore it. What do you see when you look at this time? It's more like a pyramid, right? Yeah, you know pyramids, they tend to be shorter. They're shorter than a tetrahedral shape. Tetrahedral shape means all 4 sides are equal, right? Yeah, so you see how many lines here? 1, 2, 3, 4, 5, 6. 6 lines. All 6 lines are equal in length for tetrahedral. But when you look at this shape, what can you really see in here? You can only see this part of the molecule, right? You cannot see the lone pair, remember? So pretend that it doesn't exist. This is what you can see of the molecule. The name of this shape, what we can see, is trigonal pyramidal. Trigonal pyramidal. So copy this. You need to remember this shape. What about with H2O? When we try to draw H2O, you can see that there are 2 bonding domains and 2 non-bonding domains, right? Yeah. So when we put them back where they belong, so we put O at the center. So we put H and H here. You can put also the 2 H's and the 2 other lobes. It doesn't matter. It doesn't really matter. You can put it like this, or you can put it. Let me show you because I know you might not be convinced. Okay. So pyramidal, they are not the same thing. They are not the same thing. Yeah, they are not the same thing. So let me draw this first. Because I know a lot of students will ask, hey, wait a second. What if I don't want to put the 2 H's here? Can I put them here? Or here? Or can you think of another possibility? Like here, right? I can put 2 H's anywhere I like, right? So as long as there are 2 bonding domains and 2 non-bonding domains, it's fine. Well, actually, no matter which of these you draw, the conclusion, okay, on the shape should be the same. Okay, what is the name of this shape? Remember what you can see? You can only see bond pairs, right? You cannot see lone pairs. So let's just pretend that we can't V shape. V shape. So the key point is really simple. It's just that you can see bond pairs, you cannot see no pair density. Okay? What this molecule is reduced to is this shape. So can you put down, you don't have to draw that eye in the exam, I'm just showing you this is what you see. Okay? So this is V shape or band. Okay? So that means it's very important to know how many bond pairs and how many lone pairs they are. So granted, these three molecules, they all have the same number of domains. But depending on the makeup of these four domains, whether they are all bonding domain, or three bonding plus one non-bonding, or two bonding plus two non-bonding, it can affect the determination of the shape. Great. Okay? So, yeah, just now Sarah asked, is trigonal pyramidal the same thing as trigonal planar? No, they are not the same thing. And I'm going to show you all the possible shapes you will encounter in DSE. So just like put this down first. These three shapes. Okay? Now on the next page we'll take things out a notch, even harder down. Okay, so we have let me just double check. Okay, so you can see this table actually. Okay, so you can see these tables. You will only be asked these how many total shapes are there. So there's 1, 2, 3, 4, 5, 6, 7 different shapes. Okay, so let me put this down for you here. So a summary on these shapes. Okay, if you have two domains, if you have three domains, if you have four domains, okay, so 1, 2, 3, 4. If you have 5 domains, so DSE has already simplified it already. Actually, for 5 and 6 domains, they are way more than what you see on the textbook, okay, but they have already simplified it to just these two. So now I'm going to show you the variations. When you have 2 domains, they can only be bonding domains. Okay, so they can only be 2 bonding domains. Okay? When you have 3 domains, okay, they can be 3 bonding domains and no non-bonding domain, or they can be 2 bonding domains and 1 non-bonding domain. Okay, so you have non-bonding domain here. Right. And let me finish this heading here first real quick. Okay, so you have what about for 3 domains? So for 3 domains you have 2 possibilities. For 4 domains you have 3 possibilities. And finally, for 5 and 6 domains you have only got 1 possibility in DSE. But actually it goes beyond that. Okay, let me put down the possibility. So this is possibility 1 under 2 domains. This is possibility 1 and possibility 2 under 3 domains. You have possibility 1, possibility 2, and possibility 3 under 3 domains, under 4 domains. And then you have 5 domains, and finally 6 domains. Right, so let's see what this means. So with 4 domains, the first possibility is of course all 4 being bonding domains. The second possibility is that 3 are bonding, 1 is non-bonding. The third is when you have 2 bonding and 2 non-bonding. Do you notice something? It's when you add these numbers, 3 plus 1 is 4, 2 plus 2 is 4, right? So they all add up to, 4. Okay, so they have to add up to 4, the numbers. Yeah, and for 3 domains, however many number of bonding domains and non-bonding you have, they must add up to 3, you see? So this is why I put them under 3 domain, 4 domain, 5 domain, and 6 domain. Okay, they have to be where they belong. You cannot swap the order. So and for 5 and 6 domains, there's only 1 case under each. So what is an example of molecule with just 2 bonding domains? Well, we have a lot. We have CO2, we have BeCl2, so copy a few examples. So BeCl2, BeCl2. So these are all molecules with a linear shape because they have 2 bonding domains, right? Can you see? So they are all linear. Okay, so they are all linear. Write down the name of the shape. So this is linear. Okay, they are linear. What about when you have free domains? When you have free domains, can you think of some examples? We have BF free, ALCL free. What is the name of the shape? What can you see, what can you not see? You can see all the bonding domain here, right? So what happens when you consider all of them? What is the name of the shape? They are trigonal planar. Can you see that this is like a pizza, right? Like a pizza, okay? So this is trigonal planar. So trigonal planar is therefore different from trigonal pyramidal. What about when you have two bonding domains and one non-bonding domain, like this one, okay? Like SO2. So this is SO2. Okay? What is the shape here? So you see two bonding domains and you have one non-bonding domain. So which of these things can you see, the blue or the yellow one? Only the blue one, right? So when you consider just the blue part, what is the name of the shape? V shape. Yeah, so V shape or band. So V shape or band. And for four domains, okay? So you have CH4. So we can draw CH4. And we have NH4 plus. Okay, right there. So NH4 plus. So they are all bonding domains, right? Can you see? Which means you can see them all. What is the name of this shape? Tetrahedral. Yeah, so tetrahedral. And then when we have three bonding domains and one non-bonding domain, okay, the name of this shape would be, so let me move this up a little bit. So up a little bit, okay, like that. So the example would be NH3. Do you remember NH3? Ammonia. So ammonia has three bonding domain and one non-bonding domain, like this. So which of these can you see? The blue or the yellow one? The blue one, right? The blue one only, right? Yeah, so when you focus on only the blue stuff, what is the name of this shape? I know many students confuse tetrahedral and trigonal pyramidal. Let me tell you, they are not the same. Tetrahedral has all six sides equal. Each of these lines are equal in length. This is tetrahedral. Trigonal pyramidal is not the same thing because these 1, 2, 3 sides are shorter than these three sides. So if you think that they are the same, you need to read your math textbook more. Okay. So this is trigonal pyramidal. Okay. So the six sides are not equal. Six sides not equal. I will only put it like that. And tetrahedral means all six sides are equal. Okay? And then, yeah, before I wrap this up, we have three more shapes to discuss. What about two bonding domain and two non-bonding domain? Like this one. Do you remember H2O? So H2O has two bonding and two non-bonding domains. So which of these can you see, the blue or the yellow one again? Blue. So when you reduce the molecule to just the blue parts, V shape. Yeah. So it gets better, you see, okay. It's a theory that is quite simple actually. Now finally we have 5 and 6 domains. When you have 5 domains, there's only one possibility in this level, in the SE level, okay? And this is when you have something like this. And when you have 6 domains, it's when you have this. So this is PCl5. So I think I have to draw it like this, sorry. So PCl5. All 5 are what? Are they bonding or non-bonding? Bonding. That means you can see them all, okay? So when you connect them together, what is this? Bipyramidal. Trigonal bipyramidal. Finally, when you have 6 domains, we have we have that very interesting molecule, right? The one that looks like a magic trick. Okay? It is a magic trick, okay? Because you can see that the metal like the floats, okay, floats on the gas, okay, SF6. So you have SF6. If you consider just the bonding pairs here, what is the name of the shape? Octahedral. So sadly, you need to memorize all these shapes in here. There are not many actually, it's half of the table. So you have 1, 2, 3, 4, 5, 6, 7, 8. Only 8 possible shapes in DSE chemistry. And how are you going to use this to determine the shape? If you find 6 bonding domains, it must be octahedral. If you see 4 domains, well, you have to ask yourself, are the 4 domains all bonding domains? Or are some bonding, some non-bonding? Because that will affect the shape. Okay? So I have a simple task for all of you tonight. Use this page. So there are, write down 8 possible shapes in DSE. Right, so we have 8 possible shapes. So use this page to predict the, first you need to draw the structural molecule. So draw the structural formula of and predict the shape. So draw the structural formula and predict the shape of the following. Okay, I'll review the answer next time. Okay, but I want you to try, don't just wait for the answer. Okay, so you have O, F, Q. I can tell that O is at the center, F is on the side. Okay, figure out the shape. You need to first draw using the method I taught you lessons ago. This method. You need to first figure out how many bonding domain and how many non-bonding domain there are. And then use that together with this page to predict the shape of the molecule. Okay, OF2 is the first one. Then you have like what? So you have PCl3. So you have PCl3. And finally, you have what else? Okay, you have H2S. Okay, H2S. So tell me back next time. Okay, we'll look at the other parts of microscopic world. So put down this formula, and you should be able to name it. What do we call these 3 things? The top one we call it oxygen difluoride. Have you know CO2, right? Yes. Carbon dioxide. Yes. So oxygen difluoride. Similar. Okay. Yeah. So you have oxygen difluoride. I still see a lot of students spelling this word wrong. It's fluor, F-L-U-O, not F-L-O-R. I see so many spellings like that you open my mind. Okay, so there's so many different spellings to the same word. Okay, don't spell it wrong, please. Yeah, so difluoride. What about this one? Yes, phosphorus trichloride. And dihydrogen sulfide. Okay, so dihydrogen sulfide. Is that clear? Yes. I expect this done, okay, like by next lesson. Okay? And we have tests next week on organic chem. Okay? So, right. So, yeah, again, you need to refer back to this page, where we discuss how to determine the number of bonding domain and the number of non-bonding domain. If you cannot figure out these 2 numbers, you cannot find the answer. So therefore, you have to do this correctly first. So if you don't remember how this is done, refer back to this page first. Okay? Do you know what to do? Yes? Yes. Okay, you mean the molecule. Right. Okay, yeah, then we'll continue. Okay?